Hi, everyone. So today I'm going to be talking about the Monte Carlo Tree Search, which is a search algorithm for solving certain artificial intelligence problems. The gist of it is that it is a way for an AI to think or plan ahead to achieve certain goals. Now, it's not the first decision-making search algorithm, but it is very special. And the reason is that we all know how easy it is to write programs that can do very specific tasks under very specific circumstances, given very specific instructions. It is a lot more difficult to write an AI that can kind of think on its own and figure out on its own how to solve certain problems. It's also very difficult to write an AI that can function in a very open-ended environment where there are many possibilities and many different choices. That's why we have a lot of like dumb machines that can do stuff like this, but we haven't really made any kind of walking, talking, wisecracking robots like Bender here. But the Monte Carlo Tree Search can bring us a bit closer to making smart AIs. To understand why it is more advanced, we should compare it to Minimax, which is what Deep Blue used to defeat the top chess player in '96. First, some similarities. Both Minimax and Monte Carlo Tree Search both of them use game trees, which are directed graphs that represent all possible moves and positions in a game. Think of game trees as just like any normal search tree, except the nodes represent game states. So let's say this is tic-tac-toe. If I put my X in this corner here, then the game state changes to be this node. If my opponent places his circle here, then the game state would change to be at this node. Different nodes lead to different moves being available as child nodes, just like in real life, where different decisions can affect future possibilities and what future possibilities are. The leaf nodes, they represent win or loss or a tie. Okay. Now, I don't really have much time to review Minimax, but long story short, it searches through the entire game tree or many steps ahead, uses an evaluation function to determine what future positions are favorable or unfavorable, and then assuming the opponent chooses the best possible move for himself, it will then act accordingly to put itself in the best possible position for victory. Key thing to take away is that it looks through this entire thing, every single branch, every node, and determines the best choice. If the tree is too large, then it would take way too long to do all its calculations for the whole tree, so it would limit search to all the possible positions up to a certain depth, represented by one of these lines. The bigger and more complex the tree is, the fewer turns it is able to look ahead, and basically the more stupid it becomes. Obviously, this is a problem if the problem is too complex and there are just too many possibilities. Let's say a problem is so complex that Minimax can only look one step ahead, right? Like just this next move. In that case, the AI pretty much becomes just useless. Another issue with Minimax is that if the game is so complex that you cannot write a good evaluation function to tell the AI what is a good or bad position, then of course the AI is similarly doomed. And that is exactly why, after developing Deep Blue, we could not figure out for so long how to make an AI that mastered the game of Go. Unlike with chess, Go is so complex and open-ended that an AI simply cannot brute force its way to victory. It's also very tough to write an evaluation function for the game states for Go. And honestly, this is why a lot of experts for a long time felt that it's pretty much impossible to write an AI that can master the game of Go. And that was true for a very long time. That is until 2016, when Google made AlphaGo, which defeated the world champion using a combination of neural networks, which Alyssa will talk about later on, reinforcement learning, and surprise, surprise, the Monte Carlo Tree Search. The question is, how could an AI, how could the MCTS, how could it actually plan or think ahead in a situation where there are just so many potential moves and counter moves to possibly evaluate all nodes, even with a limited depth search? The way the MCTS does it is by creating an asymmetric stats tree, which details the value of each position and adapts to the topology of the game tree. The algorithm visits more interesting nodes more often to focus its search time on the more relevant parts of the tree. And the way it sets and updates these nodes is by running simulations which start out as random and later become less so. So don't worry, I'll go through what all this means step by step. Let's say this is a hypothetical game tree for Go. All these nodes represent positions or game states. The top node here represents the board at the start of the game, so the board is empty here. And these 3 nodes represent the first, the opening move that you can make. Obviously, the game of Go is 19 by 19, so there's going to be more than 3 opening moves, but let's just pretend it's true. Let's just pretend it's just 3. So yeah, how does an AI know which move to make? It will start, the Monte Carlo Tree Search will start by making its stats tree at the starting point, which is this one right here. And it will call one of these for functions, selection, expansion, simulation, update, depending on the situation. Here, there are child nodes that it has not explored yet, so it will add a new node to the stats tree that represents the position the AI will investigate. This is the expansion phase. It will then, from that position, basically run simulations for, it will make random moves for itself and its opponent until it reaches the end, which can either be a win or a loss. And then it would call update, which updates the value of this node that it ran the simulation from. So here it would be a 1 win out of 1 simulation. It will then do that same thing for the next 2 nodes. And at this moment, the numbers say the left node is the better move, but chances are we don't really know that's true. The numbers don't really mean anything at this point because the sample size is too small. But more simulations will make it more accurate. So now it will run the selection function, and because all the child nodes have been visited, and the AI will run the select function, which determines which child node to be investigated further. What it bases the selection on is how good the stats for the nodes are and how ignored the child nodes have been as well. So what that means is if a particular node has not been explored for a very long time, it will start to place more weight on investigating that node just to make sure it hasn't missed anything. But in this case, it's going to choose this node right here because it is the most promising node out of the all 3 of the child nodes. Don't worry about this. I don't really have time to explain in detail, but basically what this means is the function this function is what allows the AI to maintain balance between exploration and exploitation. Balance between sticking to investigating promising nodes versus exploring relatively unexplored nodes. Now, because all 3 have been explored, it will purely base its selection on how good the node is. So in this case, it's the left node right here. And it will then call expansion again because this node here has child nodes of its own that has not been explored. So it will do the same thing. It will now start the simulation from the child node of the child node. It will run update, and note that here it doesn't just update the node from where the simulation started running from, but it will also update the parent node as well. And the key thing to note is that the parent node inherits the stats of its child nodes. It would do the same thing for the next few child nodes. And once the child nodes of this child, once these nodes have been explored at least once, it will run the selection from the top once again. And if you notice, the left node has a win rate of 50% now instead of 100%. But let's just assume it still chooses to select that node for investigation over the other 2 because 50% is still pretty high, and the other 2 have only been ignored 3 times. Because this node's children have been explored already, it will not run expansion again. It will run selection a second time. So from here, it will select the best one out of these nodes. And it would do the same thing, expansion, simulation, and update. And if you notice, this time it updates 3 nodes. And from this point on, it will now select. So we don't actually know how it determines. We don't actually know if at this point if it's been ignored enough to place weight on it so that it will select that node. But let's just assume, for the sake of argument, it does. So it's explored this one 5 times. So now it wants to explore some of these relatively unexplored child nodes. So it runs, it does the whole thing again for these nodes, updates. And basically, the more this goes on, the more accurate these numbers become. The more simulations, the more powerful the Monte Carlo Tree Search becomes, and the more accurately it can determine the optimal decisions. In fact, after enough simulations, the Monte Carlo Tree Search begins to converge to look almost exactly like the game trees and their values in Minimax. So basically, it's almost like running a Minimax, except it doesn't have to go through as many nodes as Minimax. If we were to tell the AI to stop right here, though, what decision or what move will it make? Well, it's clear here that it will choose to make this move. And not because it's 4 out of 7. It's not because it has 4 wins out of 7, but because it had made 7 simulations. So the more simulations, the more likely, or the node with the highest number of simulations will be selected. And so from here, the AI will choose to make this move, and then it will now build a brand new stats tree from here and do the whole thing over again to determine what the best moves are from this state, like which one of these nodes would be the best move. So one more notable point is that in addition to being effective in situations with the high branching factor, the MCTS is domain independent, which means that you don't really need to write an evaluation function for it to work. It will kind of determine on its own how to reach a win. So like the same Monte Carlo Tree Search function can run for chess, it can run for Chinese chess, it can run for, or it can navigate a maze, it can play poker, anything you want, and you don't really have to change it much, which is another reason why it's so awesome. Yeah, I basically just said that. And in summation, the Monte Carlo Tree Search is a powerful algorithm that allows AIs to solve problems in very open-ended environments. It allows AIs to be more adaptable to a variety of situations. And it works by building and updating a stats tree using simulation. Obligatory XKCD comic, but we don't have time, so I'm just going to cut it short. OK, thank you, guys. Hope you enjoyed it.